Right, so now let's understand what is Vmalloc. So Vmalloc is the another way of allocating memory in Linux kernel. The way we allocate memory using the Kmalloc. So the simple, so the another method is allocating memory in kernel driver is Vmalloc. So as the name suggests, Vmalloc means virtual memory allocation. So now the picture comes into the mind. What is the actual difference between Vmalloc and Kmalloc if both are the APIs which is used to basically allocate memory in the kernel driver? So Vmalloc basically when you will allocate memory using the Vmalloc, so Vmalloc gives you the assurance the memory will be only only virtual contiguous, but there is no guarantee that memory will be physical contiguous. So if you remember when we discussed about allocating memory using Kmalloc, so Kmalloc gives you the assurance the memory allocated will be physically contiguous as well as virtually contiguous, right? But in case of Vmalloc, whenever you are allocating memory, so there is no guarantee that memory will be physically contiguous or not, but virtually contiguous it will be. Alright. So if you check the syntax of Vmalloc, so it takes only one argument, which is the size of the buffer or the memory which you want to allocate. Alright. And for allocating this memory or using this API, you have to use vmalloc.h in your driver wherever you want to basically allocate memory using the Vmalloc. Alright. So from this diagram, it is clear like you are allocating some memory. So although it is virtually contiguous, but when you look into the physically contiguous layout of the memory, so you see this memory is scattered in like small chunks basically. So this is the one chunk of memory allocated, this is second, this is third, and this is fourth, right? So your memory is non-contiguous in physical memory, but in the virtual memory this memory is the contiguous basically, right? So whenever you want to allocate a large buffer, you should use virtual malloc or vmalloc API to allocate memory in the Linux kernel driver. The reason is whenever we are working in embedded system devices, so most of the time the memory will be short, right? So we will always have the memory constraint basically, right? So to get the memory physically contiguous, it's a bit difficult if the size of memory is large basically, right? So that is why whenever you need to allocate large memory in the Linux kernel driver, so better to go for vmalloc until unless there is some special need to get the physical contiguous memory. All right. If you know like the buffer which you are allocating, that buffer has to be only consumed internally in your driver, maybe for storing some data temporarily, or maybe manipulating some data temporarily, local data basically, right? Storing some data into the local structures, and you are very sure the memory which you are allocating that will not be having much interaction with the hardware. So there you can use vmalloc to allocate the memory, because if you don't have any interaction with the hardware, then it's okay to go for a non-contiguous physical memory. But the moment you want your hardware or DMA to operate on the memory which you have allocated, so it is always recommended to go for physically contiguous memory because the access will be easier there, right? Now which is better in terms of performance basically? So in terms of performance, kmalloc will be always better. The reason is, if you go to this diagram, so you will see whenever some request comes to access this memory, let's say if you want to access this memory, right? So for every access request coming to access this memory which you have allocated using kmalloc, like this memory is physically contiguous as well, right? So for the very first access, uh, to get this memory, you will do the virtual to physical translation basically. So let's say if you start accessing this memory from here in this virtual memory, so from the MMU you will get the virtual to physical translation. Basically you will get this address. Now if you want to access next 10 bytes or 20 bytes depending upon your requirement basically, you don't need to every time do this translation from virtual to physical, because you know this memory is contiguously allocated in physical memory also, right? So what you can do is the access or the address which you got from the physical memory, if you will keep on incrementing into that address pointer, So it will be giving you that contiguous memory access. So you don't need to do virtual to physical translation. You don't need to get the physical address for the each access which you want to make to the memory which you allocated, right? But in case of virtual memory, the scenario will be totally different. So in the virtual memory, like the memory is allocated in chunks in the physical memory. So even though if you want to access, let's say this is your 4 byte of memory, this is again 4 byte of memory. If you are if you want to access 8 byte of memory out of this virtual memory section, what you need to do is you have to first get the physical address of this memory using virtual to physical address translation. Then again for next 4 byte you have to again do this virtual to physical translation to get the address of this physical memory. Allocation happened through Vmalloc API basically. Right? So there will be extra overhead every time when you want to access the memory. You need to go for virtual to physical address translation basically. So for performance wise, you can say Kmalloc is better than Vmalloc. So that is why the concept of Kmalloc was introduced, to have a faster access to memory basically, and to have the physically contiguous memory. All right. So this is a small driver code or dummy driver code I have written, in which I am using the vmalloc to allocate the memory. So you can see here I have created one vmalloc init function. So in that vmalloc init function I am allocating 1024 bytes of memory basically. So I am just passing one argument, which is the size, basically size of the buffer. And if this allocation successful, then I am printing the address, basically the very first address, or the address which is returned by your vmalloc API. And I'm printing that address, basically the memory allocated at that particular address. Alright, if this doesn't get allocated due to some reason, so I'm just printing the error like vmalloc failed. Alright, so now you allocated memory using vmalloc. So when you are done accessing the memory, and like you don't need this memory again in future, then you should free that memory to avoid any memory leak issue. So to free the memory which you allocated using vmalloc, you have to use the API provided by Linux kernel. That API is vfree basically. Alright, and what you need to pass as an argument to this API is you have to pass this buffer address basically, which you have received as an return from allocation the memory using vmalloc API basically. So the same buffer address you need to pass to this vfree call basically. So this will be freeing the memory which you have allocated using vmalloc. So as I said, you need to use a vmalloc whenever there is need to allocate large memory basically for your own purpose. And like memory is not going to interact directly with the hardware, there also you should use vmalloc. And being a device driver developer, whenever you're writing the driver, so obviously you will know the requirement of your driver. All right, and you should also know like whether you really need physically contiguous memory or virtual memory. Virtual contiguous memory is enough for you, right? So depending upon all these requirement, you can make a call whether you should go for vmalloc memory allocation or kmalloc memory allocation. Alright, so this is the difference I have given in this table. You can go through it. We have already covered it actually. Okay, now let's discuss about another important topic about loadable kernel modules. Okay, let me go to the board. Okay, so whenever you download Linux kernel from kernel.org, so the size of kernel will be huge. The source code size of kernel will be huge actually, and it will have code which is mainlined by like all the kernel community around the world, right? And the different OEMs basically. So Samsung is adding their own code, Qualcomm is adding their own code, Nvidia is adding their own code. So there are so many companies who is basically contributing to the Linux kernel. They are adding code to basically support their own devices, right? But now let's say when you download your Linux kernel from kernel.org, and you are going to port that Linux kernel into some Raspberry Pi board, right? So the first thing is you don't need to compile all the source code basically which you received as part of your Linux kernel downloaded from kernel.org, right? It's better always to compile your kernel only with the files which is required, which is really required for you to bring up this kernel onto your Raspberry Pi board. You don't need to compile this code which is only specific to some specific vendor, right? So one way of doing this is you can use the kernel configuration to disable enable the compilation of module. You can make a decision like which module you want to compile, which driver you want to compile, or which driver you don't want to compile, right? So by going through the kernel configuration you can make decision accordingly. You can go for any kernel configuration method, maybe it's menu config, xconfig, and other methods available. All right, now when you're compiling your kernel basically, so all the modules which you all the driver or all the code which you enabled for compilation, that will be compiled with your Linux kernel itself, right? So now let's say you're compiling your kernel to port this kernel into the Raspberry Pi board or BeagleBone Black board or some XYZ board basically, right? So even you have disabled all the other module which is not required for this Raspberry Pi chipset, but there might be still some code, let's say USB, Wi-Fi, and blah blah, lot of many other driver code, which is still part of the Linux kernel compilation, but you are using Raspberry Pi board just to write some hello world driver basically for your learning purpose. So even so there you are not going to use, let's say you are not going to use USB, you are not going to use Wi-Fi, or you are not going to use a touch panel or LED or something, right? So you don't need to use these driver, you don't need to use this device, then it means you don't need to use this driver basically. But still this driver will be compiled as part of your kernel compilation, and when you will load your kernel into the Raspberry Pi board, so all these module also will be, all these driver also will be loaded as part of Linux kernel build image into your Raspberry Pi board, right? Now let's say if you want to make any change into some code which you have written. For example, let's say you have written your driver, you will call the driver is my driver, right? And this is your Linux kernel basically, which is configured for your chipset uh, to make it compilable and port to your own chipset basically. This chipset can be Samsung, Qualcomm, Raspberry Pi, Broadcom, anything basically. Okay, so now you have compiled your driver which you have written with the Linux kernel itself, right? So as an output you will get the build image. So this build image has both Linux kernel as well as your driver which you have just written, right? So what you will do is you will do first whole kernel compilation. You will flash this whole kernel image to the remote device or the target device basically, right? Then after deploying this Linux kernel into this device basically, or this SoC or the chipset, you found there is some bug with your driver basically, or you are sure okay, so there was some issue which is caused by your driver. So now what you need to do is you will again check your driver code, you will make some fixes even though you are not sure whether this is exactly going to fix your issues or not, right? You will do some fix, you will again do complete kernel compilation, then you will deploy this to the chipset, right? And then you will validate whether this fixed the issue or not. Whatever the fix you made, this is actually fixing the issue or not. If it is fixing the issue, it's fine, you can go ahead. But if it is not fixing the issue, then again you will be recompiling it, deploying into the device. You will reboot your device again and again, or you will reboot your board again and again just to validate the simple fix which you are doing. So this is causing extra overhead or making your development slow, right? So to avoid this kind of issue, Linux kernel comes with the concept of loadable kernel module. So loadable kernel module is the part of code or the loadable driver which can be loaded as well as unloaded at the runtime. Okay, which means you can compile it separately, you can load it separately, you can unload it separately. All right, you don't need to compile your kernel again and again just to make compilation of your own code. All right, you can separately compile your own code, you can separately insert your module which you compiled as a loadable kernel module into the running Linux kernel. Basically you can unload it whenever you don't need it actually. So what is the benefit of going ahead with this approach? So first of all, the the problem which we discussed, like you have, so let's say this is your my driver, you have compiled it, and after compiling this driver as a loadable kernel module you will get .ko file basically, which is kernel object file. Okay, and separately you have compiled your Linux kernel. All right, so now what you are going to do is you are going to deploy this Linux kernel into your target SOC basically. All right, so once your kernel is deployed and your SOC is up and running fine, what you can do is you can insert your driver which you have just written into the running system by using insmod command. So Linux kernel gives you this command which you can use to basically insert module at the runtime, which is insmod command. And after inserting this module you found, oh my god, there was some issue which is introduced due to my own driver, let's say, right? Or maybe the behavior which you were expecting uh, from your driver that is not meeting. So what you just need to do is you will just remove this module from the running system by using rm mode, so which is for removing the module basically. You will do removal of the module from the running system. All right, you will make change or you will make the fix, right? Again it will give you the load k of .ko module, basically the compiled kernel module basically. So again you will do ins mode, you will check whether this is meeting the expectation or not. If still you face any issue, again you will do rm mode, you will again compile it, again load it. So but to fix the issue now you don't need to compile whole kernel again and again, and you don't need to reboot your machine again and again, because after deploying or before deploying the Linux kernel or after deploying the Linux kernel to the target SOC, you will be rebooting your machines to see whether the kernel is bringing up your SOC or not, right? But in case of loadable kernel module you will be separating like separately you will be compiling your Linux kernel module, you will be loading it at the runtime, you can remove at the runtime, so debugging also is easier, right? And development process also is simple as well as optimized, right? Just to validate your simple change you don't need to compile your whole Linux kernel again and again basically. But performance wise it will not make any impact, even though you are loading your driver at the runtime, or if you are compiling your driver as the part of Linux kernel compilation itself using the older approach which we used to follow. So the working of your driver will be same, right? So the performance wise you will not see any difference, but the only difference which you can observe using loadable kernel module is like it's a optimized way of development basically. It will save a lot of your time, it will make the debugging easier. So that is the benefit you will get when you are using the loadable kernel module. All right, so now let's move to the slide. Yeah, so this is we already discussed like in the older approach we used to compile Linux kernel as well as the work code which we used to compile with Linux kernel itself, and you will get a single image which will have Linux kernel build image as well as the uh, the build libs of your own code as well, right? Drawback also we already discussed. And then we discussed about loadable kernel module versus like why this was introduced and what is the benefit of using this loadable kernel module. So as we discussed, you will compile your kernel separately and you will compile your whole your code also separately, right? So it will give you the Linux kernel build image and then your code image basically, which is the .ko, right? So there are some example of the loadable kernel module like USB code auto, and then this is for audio driver, this is for file system driver. So basically any driver you can compile and make it as a loadable kernel module depending upon your requirement basically, right? So all the benefits we already discussed, right? Yeah, so that's all I had to discuss for device driver topics. In the next session, we will go through around 150 to 200 interview questions which revolves around Linux kernel and device driver. So, as part of this training, we are not going to cover each and every topic of Linux kernel in detail. Let's say if you talk about process management, memory management, scheduling, and then synchronization, top half, bottom half. If we will discuss all these topics separately, so this comes under a like this will take again a lot of time. This itself is a complete training basically, right? So if you want to understand Linux kernel and driver in detail, if you want detailed session on that, so we have another trainings for that basically. You can opt for that. If you can go through our website and find the link. If you are not able to find the link, you just ping us, we will be sharing the link with you, okay? But in the next session when we will talk about all the interview related questions for Linux kernel and device driver, definitely you will get ideas about most of the concepts like memory management, scheduling, process management, synchronization, top half, bottom half, all those details you will get, but in form of interview questions and answers, right? But if you want to do detail, if you want to go through the detailed session of Linux kernel internal, and if you want to do some practical as well, or if you want to basically create some small projects as part of Linux kernel training, then you can opt for that training basically. All right, so see you in the next session.